In the autumn of 1958, spectators at the annual meeting of the Society of British Aircraft Constructors at Farnborough witnessed a jet age still in its nascent state. The fastest British aircraft of the day and the latest innovations in aviation technology could be examined both on the ground and overhead. Proven military aircraft like the Hawker Hunter, prototypes like the short SC-1 and the Fairey Rotodyne flew alongside the newest passenger aircraft, high-speed jets, and the latest in helicopter technology. Fairey Aviation displayed 2 rotary-winged aircraft that year at Farnborough. Each of these, they hoped, would bring them a share of the helicopter market. The aircraft seen here is their ultralight, unique among aircraft of its day. A stainless steel underfin mounted in the efflux of its engine provided yaw control. The turbine engine did not drive its rotor through a gearbox. Instead, air ducted from the engine was combined with kerosene and burned at the end of each rotor blade. Fairey called this Tipjet power, and it produced the thrust that powered the rotor. That year at Farnborough, Fairey introduced a vertical takeoff and landing airliner with a rotor powered in a similar fashion. It was named the Rotodyne. The Rotodyne was a prototype aircraft that was bold in concept and execution. Its design took several ideas from the very beginnings of rotary-winged flight and used them to build an aircraft that took off and landed like a helicopter, but flew as a gyrocopter, utilizing the rotor to provide lift in auto-rotation. To fully appreciate a project like the Rotodyne, one must first consider the history of rotary-winged aircraft the world over and their effect in Great Britain.
Things really began to happen in the early 20s, between 1925, 26, around that sort of time. And Brennan produced this very large helicopter which was driven by propellers on the tips of the blades. And that was remarkably successful and achieving, well, for the time, were quite significant flights. Now, they were only a few minutes at a time, and they were only in the hover. And it was very difficult to control with any conviction. But it was getting there, and clearly progress would have been made. However, just around that time, Juan de la Cierva brought his autogyro to Britain and demonstrated it to the ministry at Farnborough. They were highly impressed with this and decided this was perhaps the way to go. And it's rather sad that Brennan's work really rather got shelved after that. And Brennan is quoted as saying that the helicopter shall and should exist is a foregone conclusion, and I think it is irresponsible to discontinue any work on it. And Brennan's aircraft was resigned to history. Cierva became the flavour of the month. Now, of course, Cierva himself was a Spaniard, but he brought his whole project to Britain, financed to a large extent by the Weir Company. The significant thing about Cierva's aircraft are that he never ever designed a helicopter. He never intended to design a helicopter. All he intended to design was an aircraft that was proof from the stall.
Cierva's autogyro was the first successful rotary-winged aircraft, or gyrocopter. A gyrocopter does not have a powered rotor. Instead, the rotor is used to provide lift as it rotates from the forward speed of the aircraft. Although it could not take off vertically or hover, it could execute an impressively short takeoff and landing. Like modern-day helicopters, a certain degree of roll control could be maintained by varying the angle of the rotor head. An Austrian named Raoul Hafner brought his R2 helicopter to England in 1932. Hafner built the R2 with Bruno Nagler, and they achieved limited success with this design. In England, Hafner also designed and built gyrocopters. During World War II, he developed a lightweight auto-rotating system for lowering airborne forces and their jeeps to the ground. These were called the roto-chute and the roto-buggy. The R2 helicopter had a powered 3-blade rotor with collective and cyclic pitch control. The torque of this powered rotor was counteracted by 2 vertical fins placed in the rotor downwash. A rotor driven with an engine produces torque at the drive shaft. In a helicopter, this causes the airframe to tend towards rotating in the opposite direction to which the rotor is spinning. The first helicopter to truly overcome the action of torque on an airframe was Germany's Focke-Wulf FW-61. It flew for the first time with Luftwaffe test pilot Hanna Reitsch at the controls in June of 1936. The FW-61 was a twin-rotor helicopter. It is credited with being the first successful powered rotary-winged aircraft. The two rotors solved the problem of torque by counter-rotating. Effectively, each rotor produced equal amounts of torque in a direction opposite the other. This made the FW-61 extremely controllable. So controllable, in fact, that Hanna Reitsch flew a series of demonstration flights inside a stadium called the Deutschlandhalle. After World War II ended, many German engineers and development ideas went to other countries.
The helicopter industry owes a great deal to the German effort. It's not fair to say anyone cribbed anything or cheated in any way, but all progress is made by other people's progress. You don't try and reinvent the wheel every time. If someone's solved a technical problem, needless to say, everybody else starts to adapt it once the patents start to run out, and of course the patents run out with the invasion.
Helicopter manufacturers were also influenced by the pre-war designs of a Russian aeronautical engineer. Igor Sikorsky had fled to America during the Bolshevik Revolution. Before the Second World War, his VS-300 generated interest among military planners in America and Great Britain. The VS-300 was the first helicopter to utilize the main and tail rotor configuration.
World War II really brought rotorcraft work in the UK to a bit more of a standstill. There was some work with rotor chutes and the rotor buggy, which was a flying jeep using an auto-rotating rotor to bring it to the ground, heaven forbid, which they actually flew. But I think the war effort in the UK was so intense that there wasn't really any time or money to do much in the way of helicopter work. However, around that time, of course, the rest of the world was doing things. The Americans that were working quite hard, and of course, Sikorsky had produced his very practical helicopter with a rotating tail rotor to counteract torque. And the Sikorsky design really opened the floodgates for helicopter technology. And once helicopters started flying, rather like the first flight of the aeroplane, the whole thing went forward. You make progress very rapidly once you get going, and the problems start to arise, and crash by crash and incident by incident, and just pure flight development technology leads, in fact, to progress.
During World War II, the Sikorsky R-4 was developed from the VS-300. This helicopter underwent trials for the United States Army and Navy, as well as Britain's Royal Navy. After the Second World War, several companies in Great Britain began producing rotary-winged aircraft. Westland Aircraft began building the S-51 under license from Sikorsky. The Sierva Autogyro Company began work on their Air Horse. Raoul Hafner joined the Bristol Airplane Company and designed the Bristol Type 173. And Fairey Aviation began work on a project that would lead to the innovative aircraft known as the Rotodyne.
In the UK, 2 or 3 companies started to get to work. Of course, Westland Helicopters took a license out to build Sikorsky aircraft and very rapidly established themselves as a helicopter production organisation. And to be fair to Westland, they didn't just build aircraft under license. Having adopted the design, they did quite a lot to it and improved it considerably and produced their own aircraft for their own market. Raoul Hafner got appointed Chief Helicopter Engineer stroke designer for the Bristol Helicopter Company as part of the Bristol Airplane Company. The Sierva Company resurged again and started work on 2 very significant designs, the Little Skeeter and the big Sierva Air Horse. And Fairey Aviation started looking into helicopters with their Gyrodine, which later led to the Rotodyne.
During the final months of World War II, aircraft manufacturers saw the need to replace military orders with aircraft for the civil market. This was the case with Fairey Aviation. Fairey Aviation was founded in 1915 and was a primary producer of carrier-based aircraft for the Royal Navy. With the helicopter business still in its infancy, Fairey decided to test the waters of the relatively new helicopter market.
The company was obviously interested in getting into the helicopter, or certainly understanding the helicopter business, because just as an aside, Westland Aircraft, as it was then, in fact started to build helicopters designed by Sikorsky under license around about 1946-47. So there was a general desire in the aircraft business for the aircraft companies to be involved with helicopter design and manufacture.
A design team was formed at Fairey under Dr. J. Bennett, who had worked previously with both the Sierva and Weir companies. Members of the design team also came to Fairey from Doppelhof in Germany, where the first Tipjet drive helicopter had been built in 1944. The first helicopter effort from Fairey took shape as the Gyrodine. Its design replaced the now familiar tail rotor with a forward-thrusting propeller mounted on the starboard wing. This propeller also provided yaw control, and the stub wings served to offload the rotor during forward flight.
The original Gyrodine was Fairey Aviation Company's first effort to produce a helicopter as a private venture vehicle. I believe that they imported some of the engineers from Weir, which in fact, the Weir company, which took over a lot of the activities of the old Sierva company.
First flown in December of 1947, the Gyrodine performed well through its early flight trials. In June of the following year, it gained a world speed record by flying at almost 108 knots over a short course. Work was started on fabricating a second Gyrodine, and the first prototype began flight trials towards setting a speed record over a 100-kilometer closed-circuit course. However, in the spring of 1949, the Gyrodine program came to an unfortunate end.
They ran into a major problem with the Gyrodine, which ended in a catastrophic crash, which killed the crew. And that really put the end of the Gyrodine. But the second aircraft was still available. They were then looking at Tipjet drive. And they said, OK, let's adapt this aircraft as a Tipjet drive vehicle.
An investigation into the crash, I think, showed that the same standard of engineering that the company applied to its other vehicles had not necessarily been introduced into the Gyrodine. So the company decided that it would set up a helicopter design team which had the same disciplines that it used for the other fixed-wing aircraft.
A fatigue failure in the Gyrodyne's rotor head caused the catastrophe and ended the Gyrodine program. However, the second incomplete Gyrodine was used towards another development program. The rotor system for the Gyrodine had been powered with the same engine that drove its forward-thrusting propeller. Fairey Aviation had been investigating driving a rotor system through tipjets rather than through mechanical means. The decision was made to retrofit the Gyrodine as a testbed for this tipjet-driven rotor system.
We took the rotor and gearbox out of the original Gyrodine and replaced it with a two-bladed Tipjet-driven rotor. The advantage from the engineering point of view is that it completely eliminates all of the mechanical transmission.
The Gyrodine was modified to fly as a compound helicopter. It took off and landed under the power of its rotor system, but in forward flight it flew as a gyrocopter. The Tipjet-driven rotor worked by taking air from two auxiliary compressors and combining it with kerosene in a combustion chamber at the end of each rotor blade. This mixture burned to produce the thrust that spun the rotor during takeoff and landing. Twin propellers mounted on the stub wings provided forward thrust and yaw control, and the Tipjet-driven rotor incorporated cyclic and collective pitch. In forward flight, the power of the Tipjets was shut down and the rotor provided lift through auto-rotation. By the mid-1950s, takeoff, landing and transition to forward flight as a helicopter had been achieved. Although it could only sustain level flight as a gyrocopter for a short period of time, its success motivated Fairey to commit to 2 Tipjet drive projects.
Well, there are always engineering problems in any design. Of course, the first thing is that one had to provide a means of propulsion at the tip of a blade. The first thing you have to do, of course, is to get the air there together with fuel to provide a combustible mixture to provide the thrust for the Tipjet engine. So consequently, we had the problem of ducting all of the air through the centre of the rotor head, through the flapping hinge and the mechanical complexities of providing a flexible joint which didn't leak. And of course you had at the Tipjet a combustion chamber which was subjected to all of the centrifugal loading that comes on any element that is attached to the tip of the blade. There was the problem of, in fact, obtaining an outside shape which was adequate from the aerodynamic point of view, and obtaining an inside shape which met the needs of the thermodynamicists.
They learned a great deal about some of the problems they were going to meet on the Rotodyne with the jet Gyrodine. And in the meantime, they then embarked on another little project, which was the Fairey ultralight helicopter, a little two-seater, like a little glass bubble. It's the sort of thing that you used to see in some of the science fiction magazines of those days, where people were racing around in their own little private helicopter. That one was Tipjet drive, so no torque problems, and the only thing they had to do with that was to make sure they had a directional control. And the way they achieved that was they had a stainless steel fin down into the jet efflux, which deflected the jet efflux to get yaw control. John Morton used to demonstrate that at Farnborough, landing it on the back of a lorry, and coming down in auto-rotation and then flaring out at the last minute with power still on, and just flare it back onto the back of this flatbed truck.
The ultralight was built for operation from small ships with the Navy. 3 of the nimble little aircraft were built. They completed a 4-year comprehensive test program, including trials at sea and civil certification. But the project was abandoned in 1959 when the Air Ministry decided that larger helicopters would be needed by the services. A larger and more ambitious project followed the Gyrodine at Fairey as well. It was called the Rotodyne. Fairey began preliminary development on this aircraft in 1946. Their success with the jet Gyrodine and British European Airways' interest in a rotary-winged airliner helped push the project forward. In 1953, the Ministry of Supply awarded a contract for a single prototype aircraft. It would combine the takeoff and landing capabilities of a helicopter with the forward speed of a gyrocopter and the passenger capacity of an airliner.
Now, Rotodyne itself, of course, was quite an ambitious project. It was to produce a full-scale 40-seat airliner. The main thing was that it was a significant step forward to try and introduce airliner flight into helicopters. Everyone had the idea that you'd be able to fly helicopters straight into the middle of cities.
There was also a general desire in the government to promote research projects with limited expenditure in the terms of tens of millions rather than hundreds of of millions, and I think the two things came together.
The Rotodyne resembled a stub-winged turboprop airliner with a 90-foot diameter rotor mounted on its top. This rotor was powered by tipjets. For flight in the helicopter regime, the tipjets were fed air from compressors that ran off its two wing-mounted Napier Eland engines. Fuel was mixed with this air and fed to the combustion chamber at the end of each rotor blade. Once the fuel and air mixture had been ignited, the burn was self-sustaining. The centrifugal force of the spinning rotor kept the fuel flowing to each tipjet. The air compressors at each engine fed two of the four tipjets. Thus, any engine failure would not result in a full loss of power to all four rotors. Once liftoff and forward flight had been achieved in the helicopter regime, the tipjets were shut down and power was transferred to the Napier Eland engines. The Rotodyne then flew as a gyrocopter. The turboprops provided forward power, and the rotor provided lift in auto-rotation. Wind tunnel tests on a 1/6 scale model without a rotor assembly were conducted to establish the lift-drag characteristics under fixed wing conditions. An additional 200 hours were spent testing a 1/15 scale model with a powered rotor 6 feet in diameter to establish the effect of the downwash from the rotor on flight characteristics. As there were not yet any airworthiness requirements for an aircraft like the Rotodyne, Fairey chose to meet the industry requirements for both helicopters and aircraft. Design work was based on the specifications laid out in the British Civil Airworthiness Requirements for helicopters and those for fixed-wing aircraft of comparable size and performance. Gaps between the two sets of rules were covered to the best of the engineer's ability in an effort to meet any future requirements established for compound helicopters. Fairey Aviation wanted to make the Rotodyne a commercially viable vehicle rather than merely a prototype. The 58-foot-long fuselage was assembled at the Fairey facilities in Hayes. This main body of the aircraft was then trucked to the company's factory at Stockport for final assembly. At Stockport, the Rotodyne's wings and turboprop Napier engines were installed. The twin tail fins and huge rotor were attached as well. Research and development onto the rotor system had been ongoing at the company's White Waltham facility since before the Jet Gyrodine project. Now, after more than 10 years of research into tipjet propulsion, it was almost time to flight test the gigantic compound helicopter known as the Rotodyne. It was certainly large enough to fulfill both the military requirements of the Air Ministry and the perceived need for air transport from city centre to city centre. 50-plus passengers could be accommodated as per BEA's stated requirement. However, the question still remained: would it fly?
We announce the departure of Rotodyne flights to Brussels and Paris.
The Rotodyne's flight system was developed through Fairey Aviation's Jet Gyrodine project. It utilized a powered rotor for vertical flight and propellers, short wings, and the rotor in auto-rotation for forward flight. A huge four-bladed rotor was chosen for greater reliability. It was essentially an all-steel structure. The rotor head contained two concentric ducts that delivered compressed air from two wing-mounted turboprops to pairs of rotors. The 45-foot-long blades carried fuel and air to combustion chambers at their tips. Driving the rotor blades at their tips eliminated the torque and gearing problems associated with such a large rotor. In this case, gearing that would have had to handle 6,000 horsepower. The entire assembly was attached to the top of the Rotodyne by a four-legged tower, which was covered with an aerodynamic nacelle. The propulsion system was mounted to the tip of each rotor blade and was fabricated primarily from nickel alloys.
One of the keys to the success that Fairey had with Tipjets was that they did some very serious ground development work before they ever tried to put it into flight. And they established an enormous Tipjet test rig system down in the corner of the airfield at White Waltham. It was quite a fun place to work, actually, because you made so much damn noise, they kept you miles away from anybody else. So what you had was two chambers where you could actually clamp a pressure jet in as a test bed and run it in the chamber. You also had another system where you ducted air out to a rotating rig. So you had one rotating rig and two Tipjet chambers, and you could do all this test bed running down there. And of course it could be done in a fairly safe fashion without having to go into the air with it. So you didn't have all the constraints of aircraft design.
Ultimately, the combustion chambers were built from mnemonic 80, with a liner made from mnemonic 75. Air entered the chamber from the rotor blade, where it was mixed with atomized fuel. Once ignited, the mixture burned on its own until fuel was cut off. Test rigs at White Waltham were used to develop the Tipjet systems for the Gyrodine and the Fairey Ultralight, and new test rigs were built there for the Rotodyne project. Additionally, a second ground installation was established at Boscombe Down. This consisted of a rotor, power plants and controls for the Rotodyne. It was used for endurance testing and pilot familiarization. Before the fully assembled Rotodyne could take to the air, there was still extensive ground testing to be done. Fatigue testing had been extensive at White Waltham and Boscombe Down for the rotor system. However, there is more to building a helicopter than just attaching a rotor to an airframe. Helicopters are subject to structural problems related to the physical interaction between the airframe, undercarriage, and rotor systems. The entire aircraft would need to be ground tested to assess the interactions between these different structures. These ground resonance tests took place at White Waltham.
At the end of the day, the Rotodyne, albeit that it was quite a sophisticated and advanced machine, was a helicopter like any other. Vibration's a constant problem with helicopters, I'm sure you can appreciate. You stick this great rotating mass on top of the thing, and every time the rotor comes around, it puts a sort of it puts some energy back into the aircraft. And one of the major problems that you've got in the design of any helicopter is controlling that vibration and making sure it's not going to tear the aircraft apart. So you run the thing on the ground and try all the various rotor speeds and combinations of rotor speed and propeller speeds and such like, because the propellers are putting a vibration in, the engines are putting high frequency vibration in, the rotor's taking a low frequency vibration in, and all these start to club together to give various harmonics. And some of these can be quite damaging.
There is still another very great problem that the helicopter had to face, and this was a subject called ground resonance. It is a situation where, in fact, with the body, the airframe on the ground resting on its undercarriage, which of course is also an elastic entity, and the rotor rotating with blades that were also elastic members, and as the blades oscillated in the plane of rotation, you could get a situation where the effective mass of the rotating system moved offset from the axis of rotation. And if the body oscillated on its undercarriage, then in fact the axis of rotation was moving. As the rotor rotated and its effective mass became offset from the axis of rotation, it could increase the offset of the effective mass of the rotor system. as the offset of the mass increased, well then of course you had a situation where the next rotation it would increase further and further and further until the whole lot disintegrated. And the only way to prevent that occurring was to alter the phase relationships between the dynamical system of the rotor and that of the body.
The resonance testing consisted of measuring airframe response at critical points while varying rotor and engine speeds. Ground resonance was found to have some effect on the aircraft. To correct for this, the original retractable undercarriage was replaced with a fixed and braced undercarriage. One of the major contributions Fairey made to helicopter design was the development of the theories that led designers to be able to predict ground resonance characteristics for a given aircraft design. After the ground resonance tests and reconfiguration of the landing gear, the Rotodyne was ready for its maiden flight. At 22 feet tall and 58 feet long, the aircraft looked ungainly on the ground. But its huge rotor and 46-foot wingspan, covered with the Napier Eland engines, would make it a whole different aircraft in the air. Its military serial XE521 reflected the aircraft's potential for battlefield support roles and the Ministry of Supply funding for the project. A 33,000-pound maximum payload, the capacity to carry some 50 passengers, reflected British European Airways' interest in the project as well. It was on the 6th of November 1957 that the aircraft first took to the air. Test pilots J.G.P. Morton and W.R. Gilackley were at the controls of the compound helicopter. They were prepared to spend the day flying the Rotodyne strictly as a helicopter, the first of its 3 modes of operation. On startup, the turboprops fed air to the 9-stage axial compressors mounted behind them. These in turn pumped air through the tipjets and started the rotor spinning. Fuel was fed to the tipjets and the mixture was lit. Then, with the rotor spinning about 125 revolutions per minute, the Rotodyne took to the air. The flight test plan called for flying the aircraft only in its helicopter mode. After the aircraft lifted off, its yaw control was investigated. Yaw control was accomplished with the Rotodyne by varying the pitch of the turboprop engines. The first flight left all involved confident in the aircraft, and 2 additional flights were made that day. Each of these carried a flight observer in addition to the crew. Originally, the intent had been to keep the altitude of these flights within the ground cushion, but by the end of the day, the Rotodyne was making complete circuits of the airfield at well above the cushion height. The Rotodyne had performed well. The first flights had demonstrated not only the degree of control that the aircraft's engine configuration afforded, but its payload capacity as well, with 1 flight made at close to its 33,000-pound capacity. Until April of the following year, 70 test flights were made in the helicopter mode. Speeds of 155 miles per hour were achieved, and an altitude of more than 6,000 feet was attained flying under Tipjet power alone. These first flights only covered half of the flight regime for the Rotodyne. It was designed to fly as a gyrocopter as well. In the gyrocopter mode, the tip jets were extinguished, the turboprop engines were disengaged from the air compressors and used for forward flight, while the rotor provided lift through auto-rotation. The area of the flight regime that next concerned the engineers and test pilots at Fairey was the transition between flight as a helicopter and flight as a gyrocopter, and then back again to helicopter mode for landing. In that spring of 1958, the first transitions to and from flight as a gyrocopter were made. These transitions were approached methodically. At first, the coupled rotors were extinguished and declutched one pair at a time so that the rotor system was stepped from its powered mode into auto-gyration. The transitions had been made at various altitudes, and it was found that the tip jets had relight problems at higher altitudes. This was fixed with compressor blow-off valves that reduced the airflow at higher altitudes during relight. By the end of October, transitions to and from flight as a gyrocopter were being accomplished with confidence in about 30 seconds.
Prior to undertaking public demonstrations, we had obviously explored the characteristics and checked the safety of the vehicle over all of its flight regime. That was in the helicopter mode, forward flight as a helicopter, the transition from helicopter flight to turning off the tip jets to going into the autorotative mode, where we then took nearly 50% of the lift on the wing, so that we had proved the viability of the vehicle, and we were then able to demonstrate its characteristics in its different roles.
In the summer of 1958, a redesigned, retractable undercarriage was fitted to the aircraft. This undercarriage used dampers to deal with the ground resonance problem that had been discovered during the ground testing a year earlier. 6 months of flight tests had given the crew increased confidence in the aircraft. The flight envelope had been extended, and transitions from flight as a gyrocopter back to helicopter mode were now being made at altitudes as low as 300 feet. A new paint scheme was applied, and the Rotodyne was ready to begin its public demonstrations. Fairey was sure that the Rotodyne could meet the needs of its potential customers. The airlines by providing service to and from city centers, and the military in battlefield support roles. The aircraft was fast, especially for its size. It had a generous payload capacity, and its dual flight mode design lent itself to safety.
There was another nice feature about the Rotodyne. If you were in normal autorotative flight, the normal translational flight, flying along with the tip jets off, and you tried to light up and they didn't light, or you had an engine failure and you knew that you probably weren't easily going to be able to put it in the whole regime, what you could do was you could land the aircraft on a normal run-on landing just like any other airliner. And that's probably one of the big safety features of the whole aircraft, that it could adopt an aeroplane regime. And we did a number of tests doing run-on landings on the airfield, and of course you had the advantage there that you had several shots. It wasn't like the normal helicopter auto-rotation. You could come on the approach, line up, and you could be sent round again and try again, and just land it in that fashion.
Of course, flying as an autogyro enabled the vehicle to fly faster than a conventional helicopter could fly. In fact, the Rotodyne flew at 175 knots back in the 1957, which I think is still nearly is faster than most helicopters fly today.
In January 1959, the Rotodyne established a closed-circuit speed record of just over 190 miles an hour. A helicopter's forward speed is limited by its rotor blades. Forward flight has an asymmetrical effect on the rotor blades' speed in relation to one another. The forward-moving blades are actually moving faster than the retreating blades in forward flight. This difference in rotor blade speed increases with the speed of the helicopter. At a certain speed, the power requirement to move the blades and increased oscillatory stresses on the blades limits the speed of the rotor and the aircraft. These oscillatory stresses are less severe on a gyrocopter, and there is no power requirement at all on a rotor that is in auto-rotation. The Rotodyne was not limited by a powered rotor when it flew in its gyrocopter mode. In June of 1959, the Rotodyne began a publicity campaign with its first international flights. It flew from London's Heathrow Airport to the 23rd Aeronautical Salon in Paris. Stops were made at the Aravan heliport in Brussels and the Issy heliport in Paris en route to the airshow.
There were two sort of attacks on the Rotodyne project, of course. One was to see it as an airliner, flying city centre to city centre. And one of the important demonstrations they did there were the proving flights. One of the things that always brings it all back to me was the ease with which the aircraft appeared to be flown. It sort of leapt off the ground and into transition in a way as if it had been doing it 1,000 times. You didn't feel it was a faltering sort of, let's see how it goes this time, chaps. It was confident in the extreme.
From Paris, the Rotodyne went on to appear at the Aeronautical Salon. There it was met with interest by companies such as Kaman Aircraft Corporation and the Okanagan Helicopter Group. Kaman had negotiated a licensing agreement for sales and service in the United States, and Okanagan had signed a letter of intent to buy one Rotodyne with an option to purchase 2 more within 3 years. With domestic and international interest in the project growing, the Rotodyne looked to be a success.
The airliner side was more or less demonstrated at the end of the day was the flight into Battersea, of course. Battersea heliport was quite a small heliport. In fact, the landing pad wasn't much bigger than the Rotodyne. It was almost like landing on the back of a ship. And they took it into London from White Waltham. They took it in twice, actually. I wasn't on board when it did that flight. I was actually measuring noise on London Bridge, on Westminster Bridge. And I couldn't actually record the noise above the noise of the traffic, which was quite interesting because the light-up point is the time when it gets very noisy. It went into Battersea twice, very successfully, and the only comment they had from the public in general was someone rang up to say, what was this big air helicopter ending, because the little boy didn't recognize it. So that was another demonstration, all aimed at the civil market to try and allay some of the fears that people always had.
The flights into Battersea were done to dispel doubts regarding the noise levels produced by the Rotodyne. Tipjet silencers had been developed to bring the noise to within acceptable levels, but these silencers robbed the Tipjets of power. Demonstrations were also undertaken in a second area. The RAF and NATO military leaders both witnessed the Rotodyne in action.
The other area that we hoped we would sell the aircraft was to the military. We wanted to show them that there was a place for big helicopters. And the important thing was, A, to move vehicles around, B, to be able to move large numbers of troops about. And one of the demonstrations they did, of course, was the famous demonstration with the nurses. where they got about 40 nurses on board the aircraft. But that's what that was all about, to try and demonstrate the importance of the Rotodyne as a military vehicle and to show that there was a place in the battlefield for big helicopters.
During this period, design work had started at Fairey on a larger aircraft. New York Airways had expressed interest in the Rotodyne and placed an order for 5 of the aircraft with an option to purchase 10 more. This order was contingent upon the development of a larger Rotodyne. A Rotodyne that could carry up to 57 passengers. The test rigs at White Waltham were modified to accept larger Rolls-Royce Tyne engines, and a full-scale mock-up of the aircraft was under construction. However, a larger Rotodyne, designated the Type Z, would never find its way into the air. At the start of 1960, there were over 20 aircraft manufacturers in Great Britain. By 1961, these companies had been combined into 3. This government-led restructuring of the British aviation industry would delay and ultimately bring an end to the Rotodyne project. Fairey's aircraft division was merged with the Bristol Airplane Company and Westland, with Westland taking over the Rotodyne project. The ensuing corporate reorganization delayed development of the Type Z and gave potential customers the impression that Westland was not enthusiastic about the project. However, there is evidence to the contrary.
Yeovil, England, centre of the British helicopter industry and headquarters of the Westland Group of companies, now incorporating Saunders Roe Division, Fairey Aviation Division and Bristol Helicopter Division.
At the time of the takeover, Westland became the sole manufacturer of helicopters in all of England. They acquired an experienced research and design team from Fairey Aviation and even gave the Rotodyne priority over a heavy-lift helicopter of their own design. Further government support for the project was promised, but there was one condition. This support was based on the expectation of an order for the aircraft from British European Airways and a firm order from the military. These orders were not to materialize. The Rotodyne was cancelled after delays to the program due to the corporate restructuring and a lack of interest on the part of the military. With no military order, there was no government money for development of a larger Rotodyne. In turn, Okanagan and BEA withdrew their offers, and the program was effectively over. After 4 years of flight testing and £11 million invested, the Rotodyne came to an official end in February 1962. All that remains of the aircraft is a section of the airframe, the rotor head, and one rotor blade at the British Rotorcraft Museum in Weston-super-Mare. It is a historical discovery worth its weight in gold. A truly important document of German aviation history is uncovered. It is not found in the archives or by any secret military personnel after the war. It happens instead by accident. On an ordinary day for this factory worker, he discovers a sealed canister containing a drawing. It appears to be a blueprint for the design of an aircraft. On closer inspection, the document dates back to the mid-1920s. What it turns out to be are the workings of a deadly state-of-the-art bomber, illegal in Germany at that time. Its origins are inspired by this strangely designed plane. It may look backwards, but the logic behind the design is truly forward in thinking. It is one of the original tail-first Canard-designed planes, and the concept behind it demonstrates Germany's desire to be at aviation's vanguard.
In the NT, again the duck, late 20s, they had this design. Tail first, not really an airliner, but a few seats. The tail-first design would allow you to triumph against the stall. The stall was very much a feared thing. You lose control, you crash. A Canard, a tail-first design, can say that if the forward tail stalls, nose goes down, pick up speed, airplane stays in the air, all is well. The prototype flew around 1927-28, worked quite well.
It is an unconventional design by an unconventional designer. Heinrich Fokker is hoping to remove one of the pilot's biggest concerns since the birth of aviation, the dreaded stall factor. Thus, the design is catching the attention of aviation enthusiasts from around the world. Innovative as the F-19 may be, it is not without its flaws.
Eventually, it crashed. If you lose control of it at low level, it's deadly. And Mr. Wolf, the Wolf of the Focke-Wulf, he's the one who died in the crash.
With the death of their founder, and with military aircraft strictly forbidden in Germany, those at Focke-Wulf are now at a fork in the road. Do they keep on developing Canard technology for peaceful and, most importantly, legal purposes? Or do they risk both the company's future and their freedom by turning it into a deadly weapon of force? In an extremely risky decision in the history of the company, the plan for the F-19 dramatically changes. Instead of being the originally planned sports plane, it is now going to be a deadly bomber, capable of causing tremendous havoc over Europe's skies. The man behind this madness is one of Germany's true engineering geniuses. Kurt Tank, who joins Focke-Wulf as a result of a company takeover. Being there every step of the way, he harnesses and perfects this technology into what becomes known as the Model 42. The source of funding for this ambitious project in an economically starved country is still unknown. However, there is one thing for certain. Germany's quest to rule the skies is something neither military defeat nor monetary limitation can stop.
Tail-first design was developed for a number of reasons. If you have a Canard configuration, you have a very thin nose because your engine is behind the pilot. You can technically, at least in theory, increase speed with the same amount of power, which is good for combat aircraft. Also, because you have a fairly thin nose, you can improve, to a certain extent, pilot visibility.
When completed, this aircraft, powered by BMW's V12 engines and possessing a maximum speed of 200 miles an hour, is for Germany both her sword and shield. Any potential enemy will think twice about pushing around a Germany possessing an arsenal of aircraft carrying 20 200-pound bombs on board. More importantly, if Germany desires to reclaim her lost territories following the Treaty of Versailles, the Model 42 can put immense fear into both Europe's citizens and industries with its capability of causing enormous destruction. As testing rapidly advances, ironically, the rug is pulled from underneath them by neither pacifists nor neighboring European powers, but by the most militaristic regime in history. As Hitler's Nazi Party comes to power in 1933, the newly installed Chancellor's main interests are in maintaining and consolidating his power. An illegal aircraft project, if discovered, could be the end to his fragile rule. As a result, the project dies alongside German democracy. Although the Model 42's future is ended with the single stroke of a pen, the concept of Canard technology lives on. Focke-Wulf obeys the government's decision, but at the same time rapidly develops what is known as short takeoff and landing technology. One of its crown jewels is the FW-61, the world's first fully controllable helicopter. Its creator, Professor Heinrich Fokker, much like his German predecessors, symbolizes that an idea can never be defeated, no matter what obstacles it may face. Had this bomber plane been approved for production on a massive scale, one can only imagine what impact it would have had on the Second World War. It is one of the conflict's greatest what-ifs. In fighting both Britain and the Soviet Union, it might well have tipped the scale in favor of Germany. The Model 42 thus may have resulted in a soaring victory and changed dramatically the outcome of the war in Europe.
I name you hero and wish you good luck and Godspeed to all who fly in this type. Yeah? Thank you very much.
Despite the enthusiasm at Handley Page, the mood in England at this time is anything but cheerful. By 1937, the drums of war are beginning to be heard across the nation. Never has this been more evident than at these factories, where the Harrow is being introduced in an attempt to showcase Britain's military power. Unfortunately, it is technologically years behind the now cancelled Model 42. With $400 million being spent on aviation in a single year, the government assures its citizens that they have nothing to fear with this powerful weapon on their side. However, the question remains as to whether these bombers can stand up to the growing German threat. These fears are finally realized as Britain's cities are repeatedly bombed by the Luftwaffe, causing enormous destruction and loss of life. The Blitz has now focused the world's attention to what the bomber is capable of doing. The nation everyone is looking to is in dire need of a solution to this deadly problem. It may be one of Britain's most unusual designs for a plane. At Miles Aircraft, this prototype, known as the Libellula, marks not only the resurrection of the Canard design, but also exemplifies a company truly thinking outside the box.
People were very appreciative of the fact that Miles had this wonderful innovatory streak in them, and that they might come up trumps with something.
During the war in Reading, Berkshire, the factories of Miles Aircraft are working overtime, making a substantial contribution to the nation's war effort. What is capturing the imagination of the company's top designers is the reconstruction of a revolutionary aircraft. A plane that will capture massive attention with a design so futuristic that it is years ahead of its time. Hard at work with their initial sketches by ambitious and intelligent designers, the Canard plane is reborn. In this factory, British men and women are side by side, hard at work putting together this complicated design. While their soldiers are fighting on the front lines, these workers have stayed behind. Their job is to maintain the production of wartime equipment on the home front. And a mighty task for them is to construct this unusual plane possessing a tandem wing arrangement, requiring countless hours of labor. Unlike standard aircraft, the Libellula M35 has its wings at different heights and at different lengths. The reason for this is that the lesser wing acts as a forward-mounted stabilizer, thus improving control, especially in regards to landing. With its shorter wingspan and not requiring them to fold, when completed the M35 is to be used as a carrier-borne naval fighter. Its sister plane, the second of the Libellulas, with an additional engine, is intended strictly for bombing purposes. Its creator, George Miles, says that when completed, the plane will resemble a dragonfly. In just 90 days, the first plane is built, remarkable for its time. Those at Miles Aircraft are determined to see what this plane can do once it is up in the air. Getting the plane ready for flight, engineers are putting the Libellula in position. As the final inspections are being conducted both underneath the plane and in the cockpit, the company, having a huge investment in the aircraft's success, hopes to put it into mass production shortly, pending government approval. Possessing a tricycle landing gear, the intent is to achieve complete stability when landing. At the rear of the wings are the corresponding vertical and horizontal stabilizers and rudders. Once in the air, the plane is able to fly at 160 miles an hour and climb at a rate of 1,100 feet a minute. Its Canard features lend the aircraft well to both high and low-speed flight. With all of its advantages, however, the Libellula is not without its drawbacks.
So the Libellula, the problem was to control the aircraft for takeoff and landing. It had two sets of flaps with 5 settings for each set. So you had a potential 10 combinations. This was difficult because getting the right combination was one thing, because every time you changed the combination, it had some effect on the controllability of the aircraft. And it was really impractical.
Complexity becomes its Achilles heel. And despite the optimism from those involved in both the flying and the making of the plane, the military situation at the time dictates that the Libellula must come in for a political landing. In many ways, it is surprising that both versions of the design never go into mass production. However, its fate, similar to that of the Model 42, rests not on the aspiration of its designers, but on external circumstances. Britain, now with the United States and the Soviet Union as allies, is turning the tide against the German war machine. As a result, the demand for the Libellula evaporates. With prospects for the Canard design now looking all but dead, miraculously, it once again is resurrected. This time, however, it is not done by any European power. Instead, it is done across the Atlantic Ocean, in America, the birthplace of aviation. Here, the Canard design is reincarnated. The United States, referred to by Japanese Admiral Yamamoto as the sleeping giant, has awakened. Having an industrial capacity second to none, geography is the country's greatest asset. A massive labor force working uninterrupted, without fear of factories being bombed, is Uncle Sam's greatest advantage. And aircraft production is no exception. In terms of quantity, the United States is the undisputed champion. No European nation can even come close to their rate of production. However, while the country leads in quantity, it is quality that one aircraft company aspires to excel at.
But there was definitely a potential there. So Lockheed started to look at what kind of airplane could be designed around a turbine engine for high-performance aircraft.
It is Lockheed who believes it has the jet-powered solution for the fighter. One of its most secret projects of the war is the L-133 prototype, which is tested to see if this new technology can be harnessed into something tangible for the United States military. Thus, the Canard design, an important component of the project, rises from the ashes. At first, the Army Air Force show interest in the project. The emerging military-industrial complex, however, dictates the final decision, with it becoming a case of quality versus quantity that ultimately determines the project's future.
They looked at it and sort of, well, this is all very interesting, but you have an engine that's a wee bit on the complicated side, and you're producing Hudsons for the Brits, Lightnings for us, you're producing light transport aircraft, and in some cases, like Lightning, for example, your deliveries are good, but may not be quite as good as we would like them to be. And you want to get involved in the design of a new type of engine and a new type of aircraft. Please slow down. Our enthusiasm is not necessarily there.
With war raging on in both Europe and the Pacific, a policy of producing what is known and reliable is enacted. Every second must be accounted for. With the possibility of the model not functioning properly, precious time must not be spent testing the unknown. Thus, the L-133 becomes, much like the Model 42 and the Libellula, an aircraft whose potential remained unfulfilled. There is no doubting, however, with its state-of-the-art technology, the development of the L-133 would have brought Canard technology to a new level. It is the right place, just not the right time for Lockheed. To the employees at Curtiss-Wright and Canard enthusiasts, deliverance has arrived with the XP-55, known as the Ascender. With the main wings located at the tail end of the fuselage, it is certain to attract attention due to its unique design.
Presenting the Army's new Ascender plane. With its elevator controls in the nose and its motor and propeller in the rear, this push-propelled fighter reverses conventional airplane design. Developed experimentally as the XP-55, the new plane gives forward vision for the pilot and a clear path for his gunfire. In action, the darting tail-first Ascender seems to fly backwards.
Its origins lie in an Army Air Corps flirtation with unconventional aircraft design. And nothing defines the unconventional like the tail-first plane. Despite a policy of turning out proven aircraft on a massive scale, there is some room for experimenting. Originally intended as a design to be powered by Pratt & Whitney liquid-cooled H engines, it is perhaps the best chance Canard technology has of becoming more than just a blueprint or a workable prototype. Mass-scale production is the ultimate goal of its enthusiasts. After extensive testing, it appears that the Ascender is the best hope in achieving this goal. The Air Corps is impressed so far and asks for 3 prototypes to be built. The plane's future, however, comes crashing down with its first prototype. A stalling malfunction results in the first Ascender taking a 16,000-foot nosedive. As the company attempts to fix this problem, competing technology is evolving faster than XP-55. In the end, the project is cancelled indefinitely. It is not worth either the government's time or money to further pursue such a risky endeavour. Despite its name, in the end, the plane does nothing but descend into the depths of aviation history. By 1945, as Japan enters the 4th year in its war against the United States, the sleeping giant that Admiral Yamamoto feared would awake is now on his nation's doorstep. After massive casualties on both sides, American military power is successful in pushing back Japanese forces through both its superior air and sea power. The American mainland remains untouched after Pearl Harbor, with military production skyrocketing. Japan, a nation that seemed invincible in early 1942, is now feeling this incredible American force wreak havoc over its mainland. In particular, Japanese cities and their inhabitants feel the horrors of an air war that does not distinguish between military and civilian targets. American B-29s, leaving from the islands of Guam and Saipan, fly a total of 107 bombing raid missions on Japan's cities in just 1 year. One particular raid that takes place on the night of March the 9th destroys 250,000 homes and burns almost 100,000 citizens to death. In General MacArthur's historical report, he writes that the effect of these raids rocked the nation to its very foundations. With each passing month, the casualties keep escalating, with nearly 3 million people killed. Mass famine is spreading, with an estimated 10 million people suffering from serious malnutrition. Japanese Admiral Matomi Ogaki, writing in his diary on June the 18th, asks, "Does the enemy intend to destroy all of the cities in this country?" General Curtis LeMay, a key architect of this bombing strategy, pledges to bomb and burn them until they quit. The only problem for LeMay is that with a schedule of approximately 16 burn jobs on urban industrial areas every 3 to 4 days, by mid-August, American bombers will run out of cities to destroy. Japanese air forces are proving incapable of preventing this mass destruction of their homeland. A carrier raid in March of 1945 results in 161 out of 193 Japanese aircraft being shot down by American forces. Vice Admiral John S. McCain pledges to hunt down and destroy every damn plane in Japan. Despite the much-feared kamikaze tactics being employed by Japanese pilots, American military leaders are no longer planning the possibility, but the eventuality, of Japan's surrender. The maps being used by both the Joint Chiefs of Staff and the President show that whether it is through a ground force invasion or through the dropping of an atomic bomb, Japan is a nation on the brink of defeat. The only decision being made by the political and military leaders of the United States is which course of action they should embark on in order to achieve the goal of an unconditional surrender. To those Japanese military leaders who are in their last throes, their hope is to develop a highly maneuverable interceptor plane to act as an antidote against American B-29s. The Shinden aircraft, developed by Kyushu, is the only aircraft with a Canard design to be ordered into quantity production during the Second World War. Equipped to hold one pilot and having a wingspan of 36 feet, armed with 4 30mm cannons and a top speed of 466 miles per hour, in addition to its important Canard features, the Japanese military is hoping that Shinden holds the answer to solving the problem of the B-29 bomber. Work begins in June of 1944 to develop this plane, whose name translates to Magnificent Lightning. By now, however, time is not something Japan has on its side. Although the first prototype of the Shinden flies on August the 3rd, it is simply too late to prevent a devastating American attack. 3 days after it is tested, the first atomic bomb is dropped on Hiroshima. 3 days later, the city of Nagasaki is dealt the same blow. With these two bombings, in addition to the Soviet Union declaring war against Japan, the demand of unconditional surrender is met on September the 2nd, 1945, marking the end to war in the Pacific. The story of the Shinden remains one of the greatest what-ifs in Second World War history. Had Japanese production and testing begun earlier, would this aircraft have been able to stop American bombing plans as hoped? If the jet technology for this aircraft arrived in time, would the Shinden have been to Japan what the Spitfire and Hurricane had been to Britain in its time of need? For it remains an unknown piece of Canard history. The Canard design, with its origins dating back to the Wright brothers and their first flight of 1903, is a story of aviation constantly having to overcome the barriers and obstacles put in its way. It is a story of emerging and innovative technology locking horns with the politics of its time. Whether it is a result of a new government taking power, the policies of production, or of a country in desperation, Canard technology never soars above these barricades in the first half of the 20th century. There is no doubting, however, what Canard technology represents in the history of aviation. It symbolizes the innovative spirit, and it symbolizes the proud heritage of aviation. The Canard design is to be remembered through its planes and by the people that created them.
Throughout the 1950s, major aircraft manufacturers in the United States were eagerly exploring the potential of vertical takeoff and landing (VTOL) technology across various military applications. With the looming threat of intercontinental ballistic missiles and thermonuclear weapons, the military sought VTOL aircraft capable of operating from small dispersed sites without relying on traditional air bases or aircraft carriers, targets that were increasingly vulnerable to attack. A key concept driving this pursuit was the notion that an aircraft with a thrust-to-weight ratio exceeding 1 could vertically launch, transition to horizontal flight for mission execution, and then return for a vertical landing. Such capabilities promised to eliminate the need for expensive and easily targeted runways, enhancing the aircraft's survivability and operational flexibility in a rapidly evolving strategic landscape. Among the pioneers in this endeavour was the Ryan Aircraft Corporation, which endeavoured to translate this concept into a practical fighter aircraft for the Air Force with its X-13 Vertijet. However, like most other VTOL aircraft, the performance compromises made for their unique capabilities did not warrant its introduction in place of more capable conventional aircraft. The idea for the Vertijet originated just after World War II, when engineers for Ryan casually debated whether or not their FR-1 Fireball, which had a thrust-to-weight ratio of 1 at low fuel quantities, could take off vertically. The vertical takeoff idea soon advanced beyond the discussion stage. In 1947, the Navy's Bureau of Aeronautics enlisted Ryan for a contract aimed at exploring the technical complexities associated with developing a vertically launched jet fighter, a pivotal aspect of a broader initiative to assess the viability of submarine-based aircraft. Concurrently, the Navy funded a series of experimental tail-sitter aircraft comprising conventionally configured planes outfitted with large counter-rotating propellers designed to rest vertically on reinforced tail sections. Notable examples included the Convair XF-Y1 and Lockheed XF-V1, intended to utilize their high-thrust propellers for vertical takeoff from various naval vessels, thereby furnishing defensive air cover without the need for aircraft carriers. Ryan's engineering analyses demonstrated the feasibility of a comparable jet-powered design, augmented by a reaction control system capable of redirecting exhaust gases to facilitate control during hovering and low-speed flight. Subsequently, a Navy contract facilitated the construction of an unmanned flying prototype, which conducted its inaugural flight on October 20, 1950. This peculiar contraption, affectionately dubbed the Beast in the Backyard, was propelled by an Allison J33 turbine and employed a ball-mounted nozzle to provide reaction control while hovering. Ryan engineers converted a B-47 fuel tank into a cockpit to allow test pilot Peter Girard to evaluate the testbed's suitability as a manned research aircraft, which sat on its tail to take off vertically. On November 24, 1953, Girard made the first manned hovering flight in a jet aircraft with this unusual machine. After Navy funding ran out, the Air Force became interested in Ryan's experiments and in July 1954 issued a contract to the company to construct 2 VTOL tail-sitter demonstrators designated as the X-13 Vertijet. This project, based on the earlier Navy design proposal, was to demonstrate the suitability of easily dispersible VTOL fighters. Under the guidance of Chief Engineer Curtis Bates, the X-13 emerged as a compact, single-engined delta-wing fighter, with its distinctive features being a set of winglets and fixed landing gear, elements that might appear ordinary to the casual observer. Spearheaded by Robert Furman and the Ryan Technical Section, the aircraft was meticulously designed to be transported on a specialized trailer, capable of tilting vertically to facilitate the launch and recovery of the X-13 during vertical takeoffs and landings. In late 1955, Ryan successfully completed the first Vertijet, serial number 541619, and on December 10th, Girard piloted its maiden flight. Initially equipped with a fixed tricycle landing gear, the X-13 underwent testing as a conventional aircraft. Furman and his team prioritized exploring the conventional handling characteristics before risking vertical flight testing. Following the resolution of oscillation issues through the installation of dampers, engineers affixed a temporary steel tube truss with custering wheels to the rear of the X-13. This modification allowed the aircraft to assume a tail-sitting position during vertical flight testing, eliminating the need for the complex launch and recovery procedures associated with the launch trailer. Pete Girard made the first vertical takeoff and landing on May 28, 1956. On the same day, the second X-13 made its first flight. The aircraft was agile and responsive in conventional flight. As the aircraft transitioned to a nose-high attitude to achieve a hover using the thrust from its own engine, a vectorable exhaust nozzle linked to the controls provided a straightforward and efficient means of control. To facilitate the delicate landing process, small bleed air thrusters positioned on the wingtips enabled minor adjustments to the pitch and yaw of the aircraft when necessary. Integrating both conventional and VTOL control systems, a stability augmentation system ensured smooth transitions without requiring abrupt changes to pilot control inputs. During vertical takeoff, the launch procedure involved raising the bed of the launch trailer vertically. This allowed the X-13 to hang from a cable suspended by 2 arms on the top of the trailer, featuring a partially retractable hook. For vertical operations, flat bumpers replaced each of the main wheels on the fixed landing gear, preventing damage to the fuselage underside if it swung into the trailer bed, thereby facilitating transportation. Subsequently, the pilot would increase throttle until the hook lifted off the launch cable, then maneuver away from the trailer and accelerate vertically, smoothly transitioning to conventional flight. However, vertical landings posed greater challenges and were perhaps the most impractical aspect of the Vertijet concept. Its primary drawback, akin to earlier tail-sitters, lay in the obstruction of the pilot's vision by the airframe, making it exceedingly difficult to accurately gauge the distance to the ground without external assistance. Although the pilot's seat pivoted 45 degrees towards vertical during landing, the pilot still had to approach the recovery trailer blind, with the underside of the fuselage facing the surface of the trailer. Constant radio communication with a ground observer was essential to talk the X-13 into position during the cumbersome process. A 6-meter, 20-foot long folding pole with marked gradations attached to the top of the recovery trailer gave the pilot a clear indication of the distance remaining before he contacted the trailer. Once in position, the pilot gradually reduced the throttle until the nose hook caught the recovery cable. On May 28, 1956, the X-13 executed its inaugural vertical hovering flight, initiating a series of summer tests where Girard and fellow test pilot Lou Everett practiced cable catching techniques using a 1-inch thick rope strung between two towers. To safeguard against potential damage during docking maneuvers with the trailer, Ryan engineers equipped the X-13 with a replaceable wooden nose. On November 28th, Girard accomplished the first ever transition from horizontal to vertical flight and vice versa in the X-13. Then on April 11th, 1957, he launched from the trailer, seamlessly transitioning to conventional flight and executed a vertical landing, successfully fulfilling the X-13's mission profile. Illustrating the concept of dispersed operating sites, the second X-13 captivated over 3,000 military officers and journalists with an impressive display at the Pentagon on July 30th, 1957. However, competing programs diverted funds away from the project, leading to the X-13's final flight on September 30th, 1957. Despite later programs like the XV-6 Kestrel and the AV-8 Harrier achieving operational success, the X-13 provided an effective solution to the challenges of developing a VTOL fighter within the technological constraints of its era. The Vertijet successfully completed all designated tasks and undoubtedly excelled as an experimental demonstration aircraft despite the inherent impracticality of the operational concept. Ironically, by the close of the 20th century, the thrust vectoring system, originally pioneered on the X-13, would evolve into an indispensable component of advanced combat aircraft. In 1960, Ryan generously donated the first X-13 along with its launch trailer to the Smithsonian Institution. The Miles Aircraft concern conceived the M39 Libellula during the early 1940s, amid the turmoil of World War II. Initially, the concept aimed to simplify landing aircraft on carrier decks, addressing visibility challenges caused by forward-mounted engines and large wing mainplanes. A novel tandem wing arrangement was pursued to mitigate risks, resulting in a series of concepts explored by Miles during the war. The overarching term for these Miles designs was libellula, named after the taxonomic family of the dragonfly. The groundwork for this project began with the M35, essentially a technology demonstrator for a single-seat naval fighter. Miles pursued this endeavour independently, using the tandem wing setup to reconfigure the centre of gravity found in conventionally configured military aircraft. In a brief span of 6 weeks, Miles engineers introduced the M35. This aircraft was equipped with a single de Havilland Gypsy Major air-cooled inline engine, boasting 130 horsepower. During testing, the engine exhibited temperamental behaviour and longitudinal control was problematic. Nevertheless, this design provided valuable insights into the unconventional arrangement, contributing to future developments in the field. Building on this knowledge, a new design emerged, scaled at 5/8 and designated as M39B. This single-seat demonstrator featured a pair of de Havilland Gypsy Major IC air-cooled inline engines, each with 130 horsepower, showcased in outboard nacelles beneath the rear wing mainplanes. The frontal mainplane was now positioned low against the sides of the cockpit, and the fuselage boasted a finely contoured shape from nose to tail. The undercarriage transitioned to a traditional tricycle configuration. Given the larger scope of the M39B project, its dimensions were appropriately increased. The wingspans now measured 25 feet at the front set and 37.5 feet at the rear. The overall length extended to 22.3 feet, and the maximum weight rose to 3,200 pounds. As constructed and tested, the M39B achieved speeds of up to 166 miles per hour thanks to its twin-engine setup and tandem wing approach. The maiden flight for the M39B occurred on July 22, 1943. A dorsal fin was later fitted at the fuselage aft for additional control to complete the M39B's iconic three-finned appearance. Up until September of 1943, all of the work on the two aircraft, M35 and M39B, was as a private venture. From then on, the British Air Ministry decided to offer a formal development contract to Miles. Shortly after, Miles sought interest from the United States Army Air Forces, aware of their consideration of the domestic Curtiss XP-55 Ascender, which shared a tandem-wing pusher engine configuration and was intended as a fighter. The USAF's response revealed a general lack of interest in the Miles product, as the XP-55 itself faced issues, particularly with stalls and recovery. The American program only progressed to flight testing, producing 3 aircraft in total. The M39B underwent evaluation at the Royal Aircraft Establishment, encountering problems from the outset. A new undercarriage had to be installed, and several accidents necessitated constant repairs, keeping the aircraft grounded for extended periods. Despite its unconventional arrangement, overall handling characteristics were considered normal. While landing and takeoff required adjustments to the standard routine, these were deemed forgivable, and stalling and recovery performed as anticipated. In 1941, the RAF issued a new specification for a medium-class, medium to high-altitude, high-performance bomber. Miles responded with its M39 project, a modified version of the M39B featuring a pressurized cockpit for a crew of 3. The proposed power for the M39 project included either 2 Rolls-Royce Merlin 61 series inline engines or 3 Powerjets W2500 gas-powered turbine engines. This design featured a significant wingspan increase, measuring 37.5 feet at the frontal wing and 55.8 feet at the rear pairing. The overall length expanded to 35.9 feet, and the maximum weight surged to 26,750 pounds. The envisioned cruising speed was 360 miles per hour, and armament was planned to include 2 20mm cannons in the wing roots, 1 gun per root, along with an internal bomb bay in the fuselage, capable of carrying up to 6,000 pounds of bombs. Ultimately, the de Havilland DH-99 Vampire fulfilled the specified requirements. The Hawker P1005 also competed for a period. Although a prototype M39 high-speed bomber was ordered under a November 1943 contract, it was never constructed. The RAF's bomber needs were met elsewhere, leading to the termination of the M39 project, along with the data-collecting M39B aircraft. While surviving the war, the M39B lasted only until 1948, when it was scrapped. Despite its shortcomings, the Miles Libellula left an indelible mark on aviation history. Its bold, unconventional design inspired future aircraft engineers to think outside the box and take risks. The Libellula remains a testament to the power of human ingenuity and the boundless potential of innovation. The Miles M39B Libellula serves as a fascinating case study of a daring, experimental aircraft that ultimately fell short of expectations. Its unique design, ambitious goals, and ultimate cancellation offer valuable lessons for future aviation endeavours. Conceived during the latter part of World War II, the Miles M57 Aravan aimed to serve as an economical aircraft for transporting passengers and cargo over short distances, capable of landing and taking off from rugged airstrips. Development of the Aravan began in early 1944, with the vision of creating a cost-effective, low-powered freighter suitable for both civilian and military applications. George Miles, throughout the Second World War, championed the adoption of such an aircraft in the British military, challenging the prevailing reliance on gliders. After completing the development of the Miles Messenger, Miles's design team recognized the potential of a more powerful and heavier aircraft, approximately double in capacity. This envisioned aircraft could serve as a robust military transport, particularly for operations like the Burma campaign against Imperial Japan and specialized roles such as air ambulance missions. Anticipating post-war demand from civilian operators, Miles foresaw the Aravan's popularity in the civilian market. However, the War Ministry held a different perspective, delaying the project until the conclusion of hostilities and the Victory in Europe Day celebrations on May 8, 1945. The prototype aircraft was built at the Miles factory in Berkshire, debuting on January 26, 1945. The plane featured a high wing design, a high tail, and large rear clamshell doors. Miles decided that a pair of Blackburn Cirrus major piston engines would power the British-built plane. After its maiden flight, test pilot Tommy Rose gave it rave reviews for its performance. The aircraft was also capable of lifting heavy payloads, something Miles thought the Air Ministry would like. Constructed from plastic-bonded plywood with elements of spruce and metal, the Miles Aravan was a twin-engined high-wing monoplane. Its design featured a fixed tricycle undercarriage and 3 vertical tail and rudder units, resembling the Miles Messenger in its overall configuration. The wing boasted electrically actuated flaps, a recent innovation allowing adjustment to any angle. Ground steering options included both differential braking and differential operation of the throttles. The Aravan's forward fuselage had a relatively deep-sided structure, requiring a substantial fin area. The cockpit, situated beneath a large clear perspex canopy, accommodated 2 pilots, while circular windows on either side of the pod-shaped fuselage provided views for passengers. Access to the cabin and cockpit was granted through a starboard side door, with additional amenities like soundproofing often included for enhanced comfort. Known for its lifting prowess, the Aravan could carry payloads of up to 1 ton, with enough space to accommodate a typical family car, loaded through rear-set clamshell doors. The standard Aravan was powered by a pair of Blackburn Cirrus major piston engines. Alternative power plants included the de Havilland Gypsy Major and the Lycoming 0435, often necessitating the use of enlarged fins and rudders to cope with the increased power under all circumstances. By swapping the engines, the maximum speed could be increased by up to 20 miles per hour and the rate of climb by up to 50%. Work on the Aravan was resumed shortly after Victory in Europe Day. While there was immediate demand for the type amongst civilian customers, Miles were not able to keep up with the rate of orders incoming, an outcome which aviation author Don Brown attributed to the Air Ministry's decision to place the project on hold. Diverging from the prototype, the production model of the Aravan underwent notable changes, including an 18-inch elongation of the fuselage and the adoption of porthole windows in place of rectangular ones. In 1946, full-scale production of the Aravan commenced, with the majority sold to civilian operators globally. While predominantly a civilian aircraft, some military interest emerged, with Israel and New Zealand among the notable customers. Despite having a license for Aravan production in France, no such aircraft were ever manufactured in the country. In New Zealand, a single Royal New Zealand Air Force aircraft was adapted for aerial fertilizer spreading, and another for aeromagnetic survey work, though the latter proved unsuccessful. In 1957, a Mark IV model underwent research, with the Hurrell Du Bois high aspect ratio wing becoming known as the Miles HDM 105. Production abruptly halted in late 1947 due to Miles's bankruptcy and subsequent dissolution. Over the years, scientists and designers across various nations have devoted efforts towards crafting aircraft with the most minimal takeoff and landing requirements. This approach aimed to reduce the demand for expansive landing sites, thereby enhancing operational versatility. However, achieving such benefits posed significant challenges, prompting aircraft manufacturers to seek unconventional technical solutions. Among the pioneering aircraft to successfully demonstrate shortened takeoff and landing capabilities was the Ryan VZ3 Vertiplane. In the 1950s, American company Ryan Aeronautical embarked on the development of innovative aviation technologies aimed at improving these crucial flight characteristics. Leveraging a combination of established and novel technical solutions, the company aimed to produce an experimental aircraft meeting the desired specifications. The underlying technologies of this pilot project held promise for potential application in the creation of practical aircraft in the future. First of all, such a technique could interest the Army. To reduce the takeoff distance or to ensure vertical ascent into the air, different methods and designs of the aircraft can be used. In their new project, the designers at Ryan decided to apply the technology of deflecting the airflow. The wing of the aircraft of the new model was to be equipped with developed flaps of a large size that could have a significant impact on the movement of air, changing its direction and creating additional thrust. To test the original proposal in practice needed the help of a specialized experimental aircraft. The new project was assigned the working corporate designation Ryan Model 92. Following the expressed interest of the US Army in its development, a new designation emerged, VZ3, along with the fitting name Vertiplane. Over time, the military designation of the project was further supplemented with new letters, VZ3RY, under which it gained widespread recognition. The objective of the VT-plane project was to construct an experimental aircraft capable of vertical or shortened takeoff and landing. It aimed to practically test original concepts that could significantly simplify the design. The experimental aircraft wasn't intended for payload carriage or weaponization, hence eliminating the necessity for high load capacity or specialized equipment. Only elements directly pertinent to the project's primary objectives were to exhibit comparative complexity. The proposed design for the VZ3 aircraft entailed a high wing configuration with two propellers mounted on underwing gondolas and a fixed landing gear. Its fuselage featured a large teardrop-shaped elongation. Notably, the nose and central sections of the fuselage, distinguished by an enlarged cross-section, boasted vertical sides and a horizontal bottom, seamlessly integrated with other surface areas. Additionally, the tail boom sported a tapering truncated cone shape. In the central part of the fuselage, flush with its upper surface, the wing of the original structure was attached. On the tail, it was planned to install a T-shaped tail unit with a small keel sweep and a rectangular stabilizer. The nose of the fuselage accommodated the cockpit for a single pilot. In the first version of the project, the pilot was to enter through a large opening between the roof and the sides of the fuselage. Even in the initial stages of the project, it became apparent that the cabin glazing design would not offer the necessary visibility during takeoff and landing. Consequently, an additional window with glazing was incorporated into the bottom of the nose fairing, enabling the pilot to maintain visual contact with the runway. The primary innovation of the Ryan VZ3 project lay in its unconventional wing design, featuring elaborate mechanization directly influencing the aircraft's key characteristics. The proposal involved installing a rectangular-shaped high-placed wing in the central part of the fuselage. Despite its relatively modest elongation, other design features compensated effectively for this limitation. Notably, the wing boasted a substantial profile thickness. Two small-sized gondolas housing gearboxes and propeller shafts were positioned beneath the wing. These gondolas featured large trapezoid-shaped combs aimed at mitigating airflow overflow and preventing it from exceeding prescribed limits. The experimental aircraft's wing featured sizable retractable flaps, comparable in area to the wing itself. To enhance takeoff and landing performance, these flaps could extend from the wing and tilt backwards, assuming a position close to vertical. Additionally, the wing, flaps and tip ridges formed a box-shaped system designed to significantly influence aerodynamics and effectively redistribute airflow. It was due to the redistribution of the flow and the direction of the air downwards that was supposed to get a shortened or even vertical takeoff. The experimental aircraft received an unusual power plant equipped with two propellers. The Avco Lycoming T53L1 turboshaft helicopter engine with a power output of 1,000 horsepower was situated in the rear fuselage. Air intake was facilitated through a bottom-mounted intake device and an internal channel of minimal length, while fuel was sourced from built-in tanks. A shaft positioned in front of the engine transmitted power to the central gearbox, which in turn distributed torque to two shafts running parallel to the wing spars. Subsequently, power was transferred to the propellers through a series of gears. Three-bladed propellers were affixed to the shafts emerging from the underwing gondolas, allowing for the gondolas to maintain a minimal size. Their width remained consistent with the pylons on which they were mounted, thereby minimizing obstruction of the plane's surface area. Each propeller boasted a diameter of 2.79 meters, effectively covering nearly the entire frontal projection area of the wing, thereby positively influencing flight performance. The experimental aircraft of this new model was designed to exhibit acceptable controllability across all flight modes. To achieve this, it was equipped with both traditional control surfaces and non-standard mechanisms serving similar purposes. Pitch and yaw control during speed flight modes were intended to be managed by the elevator and rudder respectively, situated on the stabilizer and keel. At low speeds, such devices sharply lost their efficiency, which, in addition to them, there was developed a system of gas rudders connected to the engine. The plane couldn't be completed with ailerons for this reason. The roll control was proposed to be carried out by changing the operating parameters of the two propellers. An increase in the thrust of one of the screws caused the corresponding plane to rise upwards under the action of the increased lift force and thus led to a change in roll. The initial version of the Ryan VZ3 Vertiplane project featured a 3-point chassis with a tailwheel. The primary supports of this chassis comprised 3 tubes of varying lengths with wheels situated beneath the central fuselage section. A tail skid was positioned at the rear. Due to the aircraft's aim for minimal takeoff weight, provisions for retracting the chassis were not included. The dimensions of the first version of the aircraft were as follows: length 8.3 meters, wingspan 7.14 meters, height 3.25 meters. The normal takeoff weight was set at 1,180 kilograms, with the aircraft designed to be operated by a single pilot located in the forward cabin. The restricted takeoff weight constrained fuel capacity, with high speed and extended range not being primary project objectives. Instead, the focus was on achieving favorable takeoff and landing characteristics. The pilot project was completed in 1957, and by early the following year, the first prototype underwent testing. On February the 7th, it was transported to the airport for ground tests, which preceded its inaugural flight. Prior to this flight, extensive ground testing and wind tunnel trials were conducted over the course of nearly a year. The efforts yielded valuable insights into the aircraft's behavior across various modes of operation and identified areas for necessary improvements. According to the results of ground tests, an experienced aircraft was allowed to fly. The first flight of the experienced Vertiplane took place on January 21, 1959. The use of large flaps, together with the wing forming a box-like structure, gave certain results. In practice, it revealed the possibility of a sharp reduction in takeoff and run. At the same time, it wasn't without its problems. The initial challenges with the 1,000 horsepower engine became apparent early on, as it failed to generate the necessary thrust to take off without a sufficient headwind, resulting in extended run-up requirements. Furthermore, occasional handling issues arose under certain conditions. The primary focus of the test flights was to ascertain the actual performance characteristics during takeoff and landing modes. Evaluation of the aircraft's behavior in horizontal flight was of secondary importance. Testing revealed that the current configuration still couldn't execute vertical takeoff. Nevertheless, it showed promising potential for reducing run-up and runway requirements, albeit often reliant on favorable headwinds. Throughout the first months of 1959, Ryan Aeronautical and US Army specialists managed only about 24 relatively successful test flights. Unfortunately, during the 21st flight, the experimental VZ3 experienced a mishap resulting in damage. Despite this setback, the decision was made to restore the aircraft and continue testing. However, shortly after the accident and the commencement of repairs, the US military lost interest in the unconventional project and withdrew its participation. This decision was influenced by various factors, leading to a halt in further collaboration on the project. However, the aircraft was still needed by science, because of which, after repair, the prototype was transferred to NASA. Further work was carried out by the Aerospace Agency specialists. The tests were resumed in February 1960, but soon stopped again. During the next descent into the air, there were problems that forced the pilot to leave the car. Fortunately, the aircraft sustained minimal damage and was deemed repairable. This presented an opportunity to implement several new solutions inspired by the breakdowns and subsequent repairs. The prototype wasn't merely restored, it was also reimagined according to an updated project plan. These enhancements were informed by ground and aerodynamic tests, as well as insights gained from the initial test flights. Foremost among the changes was a significant overhaul of the chassis. The design of the main landing gear underwent modifications, and the tail skid was replaced with a fixed nose strut. This adjustment altered the aircraft's stance on the ground and during takeoff runs, requiring it to rest level with a slight nose-down attitude. Refinements to the chassis, aimed at enhancing visibility during takeoff and landing, prompted the removal of glazing from the nose fairing. Furthermore, the cabin underwent a transformation, shedding its existing glazing and roof. Now, only a small visor remained to shield the pilot, with no additional elements of the canopy present. Additionally, a portion of the metal fuselage skin in the nose section was replaced with linen material. Measures were taken to change the aerodynamics of the aircraft. In place of the crutch under the fuselage, an additional comb appeared, which improved the stability along the course. To improve the characteristics of the wing, deviated slats appeared on the plane. Also changed were the size of the flaps. Various modifications were implemented to simplify or enhance specific elements of the aircraft and improve its aerodynamic performance. By the end of 1960, NASA experts once again brought the experienced Ryan vertiplane to the runway. Inspections of the aircraft continued until 1961, primarily focusing on studying its takeoff and landing characteristics with different wing configurations, controllability in various modes, and other factors. Horizontal flight characteristics were also evaluated multiple times throughout the testing process. Over several stages of testing, interspersed with repairs, a wealth of diverse information was gathered. The prototype VZ3 was subjected to testing at speeds ranging from 6 knots, 11.1 km an hour, to 80 knots, 148.1 km an hour, and demonstrated acceptable performance across this spectrum. Optimal takeoff and landing parameters were achieved within the 20 to 25 knot range, 37 to 46 km an hour. For instance, at speeds of approximately 35 km an hour, the aircraft required 9 to 10 meters of runway, slightly more than its own length, to take off. Maintaining lift at this speed allowed the aircraft to ascend to an altitude of 1.1 kilometers. Early in the testing phase, pilots encountered the phenomenon known as ground effect. At altitudes below 5 meters, air currents reflecting off the ground began to adversely affect the operation of the propellers and wing, reducing their efficiency. Additionally, aircraft stability diminished, potentially resulting in an uncontrolled dive and subsequent crash. Incorrect use of gas rudders exacerbated these risks during such conditions. The negative impact of the underlying surface particularly hampered the implementation of the landing. Nevertheless, recommendations were soon formed on the optimal modes of descent and touching the ground. To avoid loss of control and fall, the pilot on landing, dropping below 15 feet 5 meters, had to withstand speeds of around 20 knots. Maintaining a descent angle of several degrees was crucial during landing. Experimental trials pushed the landing speed to 40 knots, 74 km an hour, and the descent angle to 16 degrees, but such landing modes posed significant risks. From the initial wind tunnel tests, it was evident that the Ryan VZ3 Vertiplane, despite its name, would not be capable of vertical takeoff and landing, a conclusion confirmed during full flight tests. Nevertheless, the project's creators achieved a substantial reduction in runway length, aligning with the original project objectives. Testing of the prototype, revamped according to the updated project specifications, persisted until 1961. Following their conclusion, American experts meticulously analyzed the amassed data, producing numerous reports and scientific works. This comprehensive study spanned several years, shedding light on various aspects of the aircraft's performance. By this time, the prototype had been relegated to storage, with little hope of resuming flights. Indeed, after 1961, the experienced VZ3 never took to the skies again. After all of the required research and scientific work was completed, the car was decommissioned as superfluous. Unlike some other unique examples of aviation technology, the only VT plane was not dismantled for metal. The aircraft was handed over to the Army Aviation Museum, Fort Rucker, Alabama, where it remains to this day. It's worth noting that the prototype Ryan Model 92 VZ3 Vertiplane wasn't the sole platform dedicated to testing and refining innovative concepts aimed at enhancing aircraft takeoff and landing capabilities. Throughout the 1950s, numerous similar-purpose aircraft were developed and tested by several other US aircraft manufacturers. Like the VZ3, these aircraft merit separate examination and review for their contributions to advancing aviation technology in this regard.